So when we moved into the world of magnetism, of course, we introduced some conventions, some simple idea, because it was completely new world for us. And then the first fundamental law which we introduced is Biot-Savart law, which allows us to find magnetic field produced by a wire with a current. So if you have a wire of any shape with current I, then of course we write down the law in a differential form, because different parts of the wire are going to be in different conditions, right? So we took infinitesimally small section ds. Let's say we want to find magnetic field at that point. R hat, it's a direction to that point. And Biot-Savart law, mu naught over 4 pi, mu naught was our new constant, and then I ds cross r hat divided by r squared. What we need to remember, direction of ds. Direction of ds is determined by the direction of the current. Basically, you need to remember that. And of course, this formula will be on the formula sheet. Although usually application of this is a little bit more complicated than the rest of the formulas. Then, if you apply this formula for an infinitely long straight wire, we can get expression for the magnetic field created by infinitely long straight wire. So, actually I should have added, so that what is r small over here, if we're interested in the magnetic field at this point, that's r, perpendicular distance from the wire to the point in question. I forgot to show you. Then, magnetic field lines, we remember, they form circles. How can we find direction of those circles? We need to apply right-hand rule number 2. Outstretch your thumb in the direction of the current and curl your fingers around the wire, so that will be direction of the magnetic field lines. Great, so after that, we found there is an alternative way of finding magnetic field using Ampere's law, which is one of the Maxwell's equations, right? So integral over the closed loop B dot ds equals to, again, our new constant times enclosed current, right? So we will discuss it a little bit. We're not going to solve any problem about this law today, because not much of a variety of problems which can be solved, and those problems which you can review from our notes of the lecture or recitation class, right? Because I can offer only, I don't know, find magnetic field created by a solid cylindrical wire or cylindrical wire with a hole, and we discussed that all, right? So you just need to review it. Great, so this and that can be used to find magnetic field, but it's not enough in order to have a foundation. So you also need to introduce magnetic force. So we introduced two formulas. This is fundamental formula, that is kind of practical. So fundamental, if you have a charged particle which moves with velocity v, and if it is exposed to the magnetic field, then of course it is going to experience magnetic force. It's just a fact which we observed. And this formula happens to work, it happens to explain the interactions between the magnetic field and the charge. F equals Q, V cross B. If you want to find direction of the magnetic force, there are like 2 steps, okay, 1.5 steps. First, you need to take a cross product, find the direction of the cross product, and then you need to quickly check the sign of the charge. If the charge is positive, this direction is going to be the direction of the force. If charge is negative, that then found direction you have to flip in order to find the actual direction of the force. Then this formula can be used. From this formula we can derive this formula. So if you have a straight piece of wire with a current, and that current, okay, that wire is exposed with to uniform magnetic field B, right, of some length L, so that length L of the wire is exposed to the magnetic field. So then we can find the sort of net force acting on this piece of wire by using, like, I, L cross B, again cross product, so we need to use right-hand rule in order to find direction of the force, right? Great, so after that we moved into Faraday's law. We found that Faraday introduced some interesting phenomena, right, blah, blah. So if you have any loop exposed to the magnetic field, and if that magnetic field, if there is a loop exposed to the magnetic field, of course there will be flux. If that flux changes in time, then somehow mysteriously EMF will be produced in the loop, right? So that's how we can find that EMF produced in the loop minus the rate of change of the magnetic flux. Magnetic flux, number of magnetic field lines crossing a certain surface. Right? This is correct for the simplest possible situation: uniform field, flat surface, and that's what most of the time we use. Then that minus allows us to find direction of the induced current and direction of EMF. Instead of dealing with that minus, we introduce Lenz's rule because it's more convenient to use Lenz's rule. So, and the Lenz's rule works like this. So, physical philosophical idea: any loop. Any loop doesn't like changes in the magnetic flux, right? So if magnetic flux is constant through the loop, then loop doesn't do anything. So EMF will be zero, current is not going to be produced, nothing will happen. But if flux, for example, start increasing flux through the loop, then of course that loop doesn't like it, and of course it starts repelling, right? So at least I compare it to that phenomenon. So basically it will start, it will produce EMF and start driving current in such a direction so that induced magnetic field, which is produced by that current, will be in the opposite direction within the loop to the direction of the external magnetic field. Again, we will practice that. Right, and then once you know direction of the induced magnetic field within the loop, you can apply right-hand rule in order to find direction of the induced current which produced that magnetic field. Then, second situation, if magnetic flux is actually going down in time, then in this case, loop becomes supportive and it tries to support dying flux. So in that case, it drives induced current in such a direction so that the induced magnetic field is in the same direction as the external magnetic field, right? And then, of course, once you know this direction, you can use you can find the induced current. Okay, so then after this, we introduce inductance. We introduce inductance as the ratio of the total magnetic flux to the current, right? And typical inductor, solenoid, right? So if you apply this formula to find inductance of a solenoid, we found this formula, mu naught n squared, where n number of loops, L length of the inductor, and A is the cross-sectional area. Right, then we also found interesting phenomena. If something happens to the current, then it's possible to produce potential difference across an inductor. Right? Although inductor is just a piece of wire, but under certain conditions, it's possible to produce potential difference across an inductor. So delta V. So if this is inductor, so current flows in, here current is out, so this is initial point, this is final point. So delta V, it's a V final potential, electric potential at this point minus electric potential at that point, right? And it is equal minus L. L is inductance of the solenoid, inductance of an inductor, right? And times rate of change of this current, basically how fast this current changes through the solenoid, right? Again, we will practice this. Great, so after this, we started slowly moving into optics. And as a first step, we refreshed, for some of you we refreshed, for some of you it's new. We introduced traveling wave equation, right? Which describes any traveling waves. Longitudinal, transverse, it doesn't matter, right? So, for example, in the case of a cord, I forgot to take my cord, right? So, in the case of a wave on a cord, y, it's a displacement of particles cord horizontal, wave propagates in this direction, and particles moves up and down, up and down. So y defines position of those particles as they move up and down. Then, but wave propagates in the x direction. So it's an amplitude periodic function, and then inside the periodic function we have a phase of the wave, which consists of kx plus minus omega t plus phi naught. K, wave number, we define it in this way. It's basically spatial frequency. 2 pi divided by spatial periodicity. Then omega, angular frequency, basically temporal frequency, and it is introduced as 2 pi divided by temporal periodicity. Right. So here 2 pi divided by spatial periodicity, here 2 pi divided by temporal periodicity. Then plus minus, plus means that wave propagates in the minus x direction, minus indicates that wave propagates in the positive x direction, right? Then there are two ways of finding speed of this wave. It's either omega versus k, or lambda wavelength times frequency. It depends what is given in your case, what you know about the wave in that case, in that particular problem. Okay, great. So then after this, we moved into electromagnetic waves. And so in the electromagnetic wave actually consists of two parts. Electromagnetic wave consists of two parts. Electric field traveling wave, transverse, and magnetic field traveling wave, also transverse wave. And together they form electromagnetic wave. In this case, electromagnetic wave propagates in the x direction, right? So all the time in the electromagnetic wave, these three directions, magnetic field, electric field, magnetic field, and direction of wave propagation, they must be perpendicular to each other all the time, period. Then also in the electromagnetic wave, amplitude of the electric field and amplitude of the magnetic field, they are connected through the speed of light. Electric field amplitude is way larger than the magnetic field amplitude. Right, so here I sketched, and pretty much electric field and magnetic field, they oscillate in unison. All the time they share ups and downs, they reach zero at the same time, at the same moment, right? So complete unison. And so here is the mathematical expression for the electric field. It's basically electric field traveling wave equation, right? So E sub y, this subscript tells us that the electric field oscillates in the y direction, but wave propagates in the x direction, right? So then amplitude, again periodic function sinus here, again wave number x. In this case, wave propagates in the positive x direction, again angular frequency, initial phase, and then magnetic field. Again, subscript indicates that magnetic field oscillates in z direction, right? But the wave propagates again in the positive x direction, of course, is for the electric field, right? And so, as I said, electric field and magnetic field, they oscillate in unison. It means that this part, sine kx minus omega t plus phi naught, sine kx minus omega t plus phi naught, exactly the same for the electric field and magnetic field. So if you know this expression, you can write this part for the magnetic field immediately, because that structure under the sine function is exactly the same. Great, so then after that we looked at the interference of any wave. And we used, for example, acoustic waves, I think. Oh yeah, of course electromagnetic waves also used, but here I used acoustic situation. So let's assume that we have two speakers, 1 and 2, right? So they create two-dimensional waves. And these are basically, I drew wave fronts. You remember wave front, collection of crests, right? And so, of course, we assume that this wave produced by this speaker and wave produced by that speaker are identical, the same amplitude, the same wavelengths, the same frequency. In that case, they interfere. And if we take, for example, this point, and we can ask ourselves, so what can we see at this point, constructive or destructive interference? In order to answer this question, we need to construct this. We need to look at this condition. 2 pi over lambda times delta r. Delta r, it's a path length difference. It's basically r2 minus r1. It's just additional distance that the second wave must to cover in order to reach the point in question relative to the first wave. Then delta phi naught, inherent phase difference. That's where students most of the time has big troubles, right? So inherent phase difference most of the time is given in the statement of the problem. If problem says 2 antennas out of phase antennas, it means that inherent phase difference is pi. If it says 2 speakers in phase, it means delta phi naught is 0. And so if you calculate this, and you will end up with m times 2 pi, where m is an integer. Okay, I forgot to write that down. M equals 0, 1, 2, 3, and so on in integer. So if you have integer number of 2 pi's, it's constructive interference at that point. If you can calculate this, and you will end up with integer plus 1, 2 times 2 pi, then it's a destructive interference. So pretty much this is the scope. So at least 60 or 70% of the exam will be based on this material, right? So, and then the rest will be, of course, based on the previous materials from the previous exams. Okay, enough of this quick review. So now problems. Let's start with, for example, this. Because application of Biot-Savart law, we solved only one problem, and we spent like, I don't know, 35 or 40 minutes solving only one problem. So it's not that trivial to use that formula. So, problem number 1. So we have two parallel wires. Okay, the first one. Let me draw it over here. So the current flows into the board, I1. Okay, I will write down the values in a second. Then there is a second current. Okay, let me position it here. I2 flows out of the whiteboard. Okay, and the values. Let me write I1 equals to 5 amps. I2 equals to 2 amps. Then they are separated by the distance d. I'll probably show it here. D equals to, I think, 6 centimeters. Okay, so now, if we take this line, we need to answer the question, at which point net magnetic field produced by this wire and that wire, net magnetic field, will be 0. So at any point, of course, you can take any point, and the net magnetic field will be a superposition of the magnetic field produced by this wire, by this current, and by that current. So now we need to answer the question, at which point magnetic field can actually be 0. Okay, so let me write that question. So what we need to find? A point. Which one? Okay, on this line, a point where magnetic field equals to 0. Okay, let me emphasize net magnetic field equals to 0. On this line. Yeah, exactly. So first of all, we need to find show magnetic field lines in order to see directions of the magnetic fields. All right, and then we will have to analyze this region, and that region. Right. So magnetic field lines created by an infinitely long straight wire. Magnetic field lines, of course, they form circles. Okay, let me draw a couple of them. The first one, let's say the second one. In direction, cross it's into the board, so I have to position my hand like this, right? And curl my fingers around. Right? So magnetic field lines are going to have clockwise directions. Right? If you're getting something else, tell me. Okay, so these are magnetic field lines. Then green. Of course, circles again. In direction, again, now I need to outstretch my thumb this way, and magnetic field lines are going to have counterclockwise directions, so this way. So now let's draw vectors in order to understand where actually 0 net magnetic field is possible. So in this region, magnetic field, you remember it's tangent to the magnetic field lines, so this will be B1. Right? What about magnetic field created by the green? Actually, I can draw this one of these green magnetic field lines. It will go sort of like this, right? And direction of this magnetic field will be this way, B2. Right? So over here I drew one of these magnetic field lines which would go, for example, through that point. So, so the question is it possible to have 0 net magnetic field in this region to the left from current I1? First impression, kind of correct. It looks like, yeah, because we have B1 this way, B2 down. So it looks like, yeah, they sort of try to cancel each other. But what about magnitude? Now we need to be careful. Look, I1, current I1 is larger than I2. Okay, actually we need to, of course, let me write this formula so that I can use it. So B equals mu naught times I divided by 2 pi r. Look, so what about strengths of B1 and B2? B1, since current I1 is larger, B1, is going to be all the time stronger than B2. All the time, because B2, you see, it is created by I2. I2, the value of the current is smaller. And the distance to that point, to those points all the time is going to be larger for the second current. So, all the time, B sub 2 is going to be smaller than B sub 1, although they are in the opposite directions. But B sub 1 is going to be all the time larger than B sub 2. So, cancellation is impossible. Complete cancellation is impossible in that region. You see that? Okay, so let me write that in some reasonable words. So in this region, B net is not equals to 0. Impossible. So, impossible. And let me write, so, since I1 is larger than I2, and the distance R1 is smaller than R2. So the distance is smaller and I1 is larger, so of course B1 is going to be larger than B2 all the time. Right? So B1 is larger than B2 all the time, always. So in this region, it's impossible. Now, between these two wires, direction of the blue magnetic field, blue down, so it's a B1, and the direction of the green magnetic field, which is B2, also down. Now definitely it's impossible, obvious, right? So since they're in the same direction, of course, they add each other. So cancellation is impossible, right? So let me write that down also. So for this region, what I wrote, B net is not equals to 0 since B1 is parallel to B2 all the time. In order to have cancellation, they must be in the opposite directions. Right? So again, impossible here, impossible there. So now the last region, to the right of the wire 1. Right? And here, again, let's look at the directions. So now also let me draw also magnetic field line produced by this current I1 over here. Right? So it will be something like this. I can do better than this. Okay, something like this. It's one of these magnetic field lines, right? So blue magnetic field is down, B1. Green, you see, magnetic field lines has counterclockwise directions, so B1 will be, B2 will be up. So opposite directions, like over here. But now let's look at the magnitudes. So B2, the current, B2 current is smaller than I1, but the distance is small. So distance is smaller, making magnetic field 2 stronger. Right? So as a result, balance of smaller current, but also smaller distance, it's possible for B2 to be on the same value as B1. Because B1, yeah, it's kind of stronger current, but the distance to the point in question is larger. Right? So it's possible that B2 is equal to B1. So now let's write down actually expression in order to find the distance to this point where magnetic field is 0. Right? So let's assume that this is the point where magnetic field is 0. And let me label this distance. You know what, let me use red. Label this distance, because this is our unknown, effectively, x. Distance from this wire to the point in question. So I assume that magnetic field B2 and B1, 0. I mean, they're equal at this point, and of course net magnetic field will be 0. So I assume so let me write something like this. Assume that B net equals to 0 at the distance x from I2, from this point. Okay, so now let's write down. So B net equals 0. It means what? B net equals 0. It means that B, which way? B2 or B1? I wrote, okay, B2 at point x minus B1 at point x equals to 0. Right? So at this point, so B2 minus B1 equals to 0. So it means they're equal in absolute value. So it means B2 at this distance at this point x equals to B1 at point x. So now this is the expression which we can use to find the value of the magnetic field. So let's apply it for B2. B2, so it's a mu naught I2 divided by 2 pi. Which distance? R equals to what? Our point in question is at the distance x, our unknown. So R equals x for this B2. So times x. So now B1, mu naught times I1 divided by 2 pi. And now what's the distance? So it's a distance from this point to this point, from the point where I1 to the point where we assume magnetic field, net magnetic field is 0. So this distance consists of d plus x. You see, d plus x. Okay, so d plus x. Okay, so we have one equation and how many unknowns? Given, 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 x unknown, given, 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 x unknown, one unknown. So we should be able to solve it. So pretty much now it's just a question of solving it for x. So mu naught, of course, can be cancelled. 2 pi also gets cancelled, and as a result we have d plus x I2 equals to x times I1. So I just multiplied this by that and this by that. Okay, so x over here and over there, so we need to combine them. So it will be di2, and this I will move to this side. So it will be x I1 minus x I2. And of course x can be factored out. So x I1 minus I2. And just simple manipulations. So x will be this divided by that. X equals to di2 divided by... Wait. You see something? I1 minus I2, right? So I wrote x2, I2. So I1 minus I2 is in the denominator. So that's the expression for the distance at which net magnetic field It's going to be 0. So if you plug numbers, we can write it in centimeters. So 6 centimeters, and then the ratio of these currents I2 is 2 amps, and divided by I1 5 minus 2 amps. Here 3, 6 divided by 3, 2, 2 by 2, 4 centimeters. Will be 4 centimeters, right? Yeah. 4 centimeters. That's the distance at which net magnetic field is going to be 0, or B1 and B2 are going to be equal in absolute value. So pretty much here, so we practiced finding directions of the magnetic field lines, analyzing their values, right, and also practice using this formula in a reasonably simple mathematical expression. Make sense? Great. So, I think it's enough. Usually students don't have significant troubles with this formula, right? Again, as I said, this is more complicated. So now, probably one conceptual question about Ampere's law. So now let's look at Ampere's law. And then magnetic forces. Okay, I will start erasing it slowly. Okay, I'll keep that for now. So number 2. So what if we have this situation, these 4 currents? It's more like a conceptual question, right? Not a full problem. But nevertheless, okay, so let's say current I1, then current I2, let's say here. I2 current here, then I3, and I4. So 4 currents. And they all have the same value. I1 equals to I2 equals to I3 equals to I4, just for the sake of simplicity. 2 amps. Then let's assume then that we take this loop, closed loop. Oops, we need to close it. And we need to calculate this integral. So we need to find, find integral of b dot ds. We just need to know the value of this integral over this loop, over a given loop, given loop. And actually, direction was also given, direction of integration. So here I drew this loop, and direction of integration is this one. Right, so let's say this is direction of integration. So we need to find this. So it's a basically direct application of the Ampere's law. We just need to find the left-hand side of the equation. That's it, right? So in this case, we don't need to actually integrate it. So Ampere's law, integral of b dot ds equals to mu naught times I enclosed. So that's our unknown. So we just need to find the total enclosed current carefully with proper signs. so I can erase now this. So, mu naught times all enclosed currents. I4 not enclosed. Not enclosed. So we can skip it. So we have only three currents, I1, I2, and I3. So, and of course some of them must be positive, some of them must be negative. So the rule which we have to follow in order to get the correct sign for each current. So since direction of integration is given, basically this Amperian loop over this Amperian loop. So now basically we just need to use right hand rule number 2. So you curl your fingers in the direction of integration, and your outstretched thumb gives you a positive direction for the current. So in this case, into the board, positive direction for the currents. So it means that I2 will be positive, I1 negative, I3 negative. Let me try to draw the picture. Horrible picture of my hand. For
Wait, hand. Thumb goes in.
in. Okay. So it means that which way I wrote it. Okay, I explained this. So this is into the page. Into the page. Because I cannot draw a three-dimensional hand, no way. Even two-dimensional, it looks ugly. So, into the page, so as a result, let me write, so I1 is negative, I2 is positive, and I3 is also negative. Okay, so now let me write over here. So it will be I2 minus I1 minus I3. Yeah, so now it is equal to mu naught 2 amps minus 2 amps minus 2 amps, because all currents are the same, all currents are the same. So as a result, we're getting, it will be minus 2, I will use units, right? 2 amps times mu naught, in terms of mu naught. Again, the point of this question is just to remind you about this right-hand rule, how we can find, how to connect direction of the integration with directions of currents, because that's what usually students forget the first, and then the rest, with time, of course. And of course, with faculty, it works the same way. If you don't use something for quite some time, you start forgetting it. It's absolutely normal and nothing wrong with that. We remember on this something which we used almost every day. Next example, as I said, it's just basically applying Ampere's law to find magnetic field created by an infinitely long straight wire or with the hole. I'm not going to repeat those examples, right? You can open up your notes from the lecture or from the recitation class. Pretty much there are only that type of problems which we discussed. So I don't want to repeat. If you want, here in my notes, you can look one more time of what we discussed in the lecture. Okay, enough of this Ampere's law. Now, forces, magnetic forces. First conceptually and then actual problem. Should be enough. Almost a conceptual question. So, 3. So let's do this. Let's assume that this is our infinitely long straight wire with a current I. And now I will drop a few charged particles around this wire, and we will try to find direction of the magnetic force. directions of magnetic force. So first, let's assume that this is first particle. Let's say positively charged, Q. And we want to find direction of the magnetic force acting on this particle. Right. So, application of this Lorentz force. So we need to first find direction of the magnetic field, because this charged particle exposed to the magnetic field. Aha. Okay. Now, who sees what I forgot to draw? Very important. Without that important piece of information, my question is completely, I don't want to say stupid, but close to that.
The magnetic field?
Yeah, I will draw that magnetic field soon. Yeah, definitely, because there is a current with the wire, so there will be magnetic field. Very important piece.
The velocity of the charge.
Exactly. You remember, I told you several times, in the world of magnetism, everything is in dynamics. In order for a particle to produce magnetic field, it must fly. In order for a particle to experience magnetic force, it must fly, it must move. So right now I just drew a particle, right, and started thinking about actually finding the force, and then I realized that essential information about our particle is missing. Velocity. Velocity must be shown. Let me look which velocity I used in my picture. That way. No, this way. So, this is velocity. If velocity were zero, what will be the net? What will be the magnetic force? Zero, of course, exactly right. So, velocity is zero, force is zero. If you just take a particle, a stationary particle exposed to the magnetic field, nothing will happen. The particle will completely ignore the existence of that magnetic field. So now after this, yes, now let's find direction of the magnetic field. So that right-hand rule number 2, outstretch your thumb in the direction of the current. So and curl your fingers like this, right? So it will be okay. Let me draw this way. So these are magnetic field lines and directions. Here it's towards us, below, away from us. So it means that I should have used different color. Okay, but anyway, realize it later. So out, here it's out of the board, out, dot. So that's B. And let me check, yeah. And here, of course, we're going to have crosses. So that's B. Right?
This is
Mm-hmm.
magnetic field, right?
So this is our wire. This is direction of the wire. I mean direction of the current towards me, right?
Yeah.
So you need to outstretch your thumb in that direction
Yeah.
and curl your fingers around, basically like grabbing it,
Yeah.
right? Yeah. So you see above, this is wire above. Magnetic field is out of the board towards you, dot.
Yeah.
Below, into the board, away from you, crosses. And so, once we know direction of the magnetic field and direction of the velocity, now it's just a question of application of that force. So let me write underneath. So F equals Q V cross P. So now, right-hand rule first, we need to find direction of the cross product, V cross B. V that way, B is into the board. I need to adjust my body. So I have to position my hand like this. So first, along the first vector in the cross product, right? Then adjust your orientation so that you can naturally bend your fingers. Dot is towards you. So my position is wrong. Orientation is wrong. I need to position like this. Right? So V, and now I can bend my fingers in the direction of magnetic field, which is towards you. V cross B. So cross product V cross B looks like down. Getting the same? And since charge is positive, so that direction of V cross B gives us a direction of the magnetic force. Right? Because again, if I position my hand like this, then magnetic field that way, no. See? Did you get the direction? Okay, cool. Right, and let me check my notes. Yes. So it is down. So F.
Just make sure that that's magnetic field, right?
No. That's magnetic force. Magnetic field is out.
Oh,
Dot.
Oh, yes.
Dot is out. It's like an arrow flying towards you. You
oh
see
yeah,
that?
so that's just force. Alright.
V cross B down. Okay, so next particle. Let's assume that that particle over here, let's assume it's negatively charged, and it flies up. Okay, why not? V. Okay, direction of the force. So first, direction of V cross B. V is up, B is towards you. So I have to adjust myself, I have to position like this, right? Yes, where to go. So up, V in the first vector. V cross B. So what's the direction of the force eventually? Eventually, direction of the force?
So left.
V cross B is to the right. You're right. Yeah, you're right,
Oh.
that way. V cross B that way. But since the charge is negative, we need to flip that direction. Right? So don't forget that about that additional step. Check the sign of the charge. Because quite often, even good students on the final exam, I saw they make this silly mistake, right? Because they usually worry about the right-hand rule. Once they find that, they feel okay, excited, they jump to the conclusion without checking that additional small step. So let me show. So first, this will be direction of V cross B. Okay, I already forgot what's the direction. So V cross B that way. So this is the direction of V cross B, but since charge is negative, so the actual force is this way. Don't forget about that. Yeah, as I said, I will try to record it when if everything works fine. So of course, I will upload it. So now next, let's say this is positively charged particle over here, plus levels. What again? Upward. So V. So again, V cross B. B is cross. It's into the board. Yeah, cross. V cross B. Right, V cross B. So V cross B that way, and since charge is positive, that is the correct direction for the force. Right? So this will be direction of the magnetic force. Did I get this? Yeah.
I have a question. How come for the one up top, you put your hand like this, and for the one on the bottom, you put your hand like this?
Okay, I don't remember how, but I just tried to match directions of the vectors which are involved in the cross product. Pretty much these two vectors, V and B. So first, V is up. So I just need to position my hand up. What orientation right now, I don't know. So now, in order to get the correct orientation of my hand, I need to look at the second vector in the cross product, B. So B is dot towards you. So I have to position like this, my palm that way, so that I can naturally bend my fingers in the direction of this vector B.
Oh, okay.
Direction of vector B determines, right, so orientation. So if I position like this, no way I can bend only with.
Wait, for the Q where we got the cross product, B is going towards.
B towards you in the upper part.
So I thought that V,
V.
yeah,
Uh-huh.
and then B,
B, yeah, so you're talking about, yeah, absolutely correct.
and then but the force is going this way.
No, charge is negative.
Oh, so you flip it.
Yes, of course. If the charge is positive, direction of the cross product gives you direction of the magnetic force. But if charge is negative, your found direction must be flipped to the opposite one, right? Okay, so over here, since magnetic field towards you, I have to position my palm this way. But here, so direction of the velocity is the same.
So it's like this.
But I need to now position myself like this and palm that way facing because magnetic field here below into the board. So in order to bend my fingers into that direction, I need to position it like this, right?
That's it. Thank you.
So it's all about these vectors, two vectors, V and B, their directions, their directions. Okay, so now the last question. Okay, still running. So now next vector, one more, I mean not next charge. And after this it should be enough. So let's say this is our negatively charged particle, Q, and it moves this way. So finally, what's the direction of the force? Do it by yourself. And then 1 minute, and then I will do it. So what's the direction? Up, you think?
Or up.
Up, yeah. I have no idea. Of course I have it in my notes, but
For which one again? It's for.
this, the last one. So V that way, then B is into the board, so I have to orient my hand like this, right?
Oh,
So
it's
V.
into the board, yeah.
And then in order to bend my fingers into the board, I have to position my hand like this,
That's
orient.
negative. So what the force-
So V cross B is down, V cross B, but since charge is negative, up. Again, let me show in this case both directions, V cross B, and so this is V cross B, but the force, of course, will be up. Almost every exam I give questions related to this fundamental formula for the magnetic force. It's one of the foundations, part of the foundation. It should be enough. It should be enough, right? Now, make sense?
Yeah.
Great. Right. So now, so this is basically conceptual, and now the problem. So, 4, I think. Okay, so I need to draw a nice picture over here. Right. I will start with the picture, and then I will start writing actually what is given. So this is a wall. Then there are 2 springs. And over here there is a wire with a current. Current goes this way. And actually, eventually, we will have to find the value of this current. Actually, to some extent, this system which I'm going to draw can be used as a crude ammeter device which can be used to measure current. Then, spring constants are given. Right, so let's say K, okay, I will write the values. Then, the whole thing is exposed to the uniform magnetic field. Magnetic field is towards you. So that's B. I think now it's time to start writing the values of all this. So we have two spring constants are, okay, let me write K1 equals to K2 equals K equals to 10 newtons per meters. Then magnetic field, 0.5 Tesla. Direction is shown. Then this wire, that part of the wire which is exposed to this magnetic field, maybe I can even, no, I don't want to outline. So this length is L. So magnetic field from this line to that line, so and the length, or the width of this magnetic field area is 20 centimeters, 0.2 meters. 0.2 meters. So what else is given? Okay, there is another thing is given, but in order to introduce that, I need to discuss the dynamics of this problem. So right now it's an equilibrium position of this wire. Equilibrium, so of course there are some forces, several forces acting on this wire. So there is a spring force, there is a spring force, but also there will be a most likely magnetic force, right? And those three forces gives position, they give position, equilibrium position of the wire right now. But if we, for example, turn the current off, what will happen to this wire? It will be pushed this way to a new equilibrium position. So, distance from that old equilibrium position when the current was off and this new equilibrium position when the current is on is given distance. Okay, let me show this. This is, probably I'll just use dash line. Yeah. Dash line. Right, so that is, let me write, so the wire is here, the wire is here, or was here when current was equal to 0. Actually, it's basically very simple. If we turn off the current, magnetic force, of course, acting on the wire will be 0. And there is two spring forces which will push this wire to this position. So this is the equilibrium position of this wire when the current is off. When you turn the current on, the wire will be pushed that way because of the magnetic force, and this is a new equilibrium position for the wire when the current is not 0. So this distance, delta x, is given. So delta x, what's the value? 1 centimeter. So this distance is delta x, and that delta x is 1 centimeter. Of course, at some point we will have to convert it into meters, but that will be later. So this situation. Now I gave you everything, and again we need to find the value of the current. Again, let me check if I give you everything. Yeah, let me write what needs to be found. So find I. We only know about this current, direction of the current. Maybe you connected it over here to the battery, so you know here positive electrode, negative electrode, so basically you know the direction of the current. You just need to know the value of this current. So of course, where to start? And we need to start from something fundamental. And then we will start diving deeper and deeper, and we will eventually, eventually current will pop up. So, does this problem reminds you of anything from Physics 1, at the end of Physics 1, where you solved problems about static equilibrium? Do you remember fundamental equations which you used in order to start solving problems about static equilibrium? Usually students don't remember at this point, but of course once I see James kind of nodding, he knows, right? Okay, yeah. I believe that. So, let me push you to the correct formula. Actually, you all know that. Which law can be used to find, or okay, not to find, to describe motion of any classical mechanical system? Which fundamental law can be used to describe motion of any classical mechanical system? Again, the Disney world of quantum mechanics is completely different, so we're not discussing that. It's completely weird, right? So, classical mechanics only. Which law? And you all know that law. You know? You do know, actually.
F equals ma.
Newton's second law, F equals ma, sounds so kind of diminishing. You need to glorify it's a Newton's second law, right?
Okay.
Equation of motion, right? F equals ma, it sounds solid. So yeah, Newton's second law, F equals ma. So let me write it down. So that's the beginning. Motion of any system can be described by, okay, net force acting, net force equals to m times acceleration, right? Now, can we use this law to describe no motion situation? Why not? What is no motion? It's a special case of a motion, right? So what do we have to adjust in our Newton's second law in order to describe no motion situation, stationary situation? If something is stationary, if I'm staying, what's my acceleration?
Zero.
Zero. Of course, that's it, right? So for no motion, acceleration equals zero, and we're getting that beginning of the solution of any static equilibrium problem. That's what you've done in Physics 1 at the end of Physics 1 many times, stabilizing some beams or ladders against the wall or signs, right, hanging from somewhere, right? It's all from the Newton's second law. So, in our case of a static equilibrium, okay, of an equilibrium, acceleration equals to zero. So let me frame, this is important, right? So as a result, we come to the beginning of the solution. That's the beginning of the solution. So right now, current is not even close to us, right? But that's the beginning, and we start diving deeper and deeper and deeper, and at some point, current will pop off. And only then, when everything will be revealed, we will start seeing what can be done. But for now, yeah.
So it says in our case.
In our case of an equilibrium. First, I thought about writing something different. Acceleration equals zero. So that's the beginning. So now you understand what needs to be done. We need to identify all forces. And since forces are vectors, let's introduce coordinate system. Because we need to know which forces are positive, which forces are negative. All right, so let me introduce coordinate system. This is x. And I will position origin at the point where the wire is when the current is off. Okay. So now, let's identify forces. Spring force. Springs are compressed because they are not compressed when the wire is here. So right now, springs are compressed. So there will be two spring forces acting this way. F spring and F spring, because we have two wires. What did I say? Two wires. Two springs. Sorry, guys. Two springs, because there are two springs. Sometimes there's a decoupling between my brain and my tongue. It happens. All right. Then, what about something else, another force? Magnetic force. if there is a current, a wire with a current exposed to the magnetic field, then of course there will be magnetic force acting on the wire. We have straight piece of wire with current exposed to the magnetic field, of course there will be magnetic force. So what's the direction of that magnetic force? We need to look at the cross product. F, you know what, let me write down underneath. So F magnetic, I, L cross B. Spring force easy, right? So let me write F. Spring equals to, minus Kx. So let me write absolute value because we will discuss K delta X. Absolute value. We see the direction. So now, direction of the magnetic force. What determines direction of L? Direction of the current, right? So since current is down, so that's the direction of L vector. Absolute value of L is this L, right? That part of the wire which is exposed to the magnetic field. Right? So now let's look at the cross product. L cross B. L is down, B is dot, it's out. Dot is out, yeah. So L cross B, right? L down, B towards you. So magnetic force is that way. And in this case, there is no additional step because current can be only positive, right? It's not like in this formula QVB, we were checking the sign of the charge. Here, current is absolute value of the current in this formula. So, you getting that way? L cross B?
So L down,
L down,
so that means
B is that way, so you have to position, yeah, exactly. So your thumb gives you that direction.
see that's magnetic force.
Magnetic force acting on this wire. So magnetic force, and actually it makes sense. F magnetic, because when you turn this current off, this magnetic force disappears, and these two spring forces will bring this current to this position. When you turn that on, magnetic force will push the wire to your left. It makes sense. That direction makes sense completely. Right? Okay, so now direction to the left. Now let me write absolute value of the magnetic force. I, L, B, and sine. Sine of which angle? Sine of the angle between L and B. Direction of L, down, B, out. The angle? 90 degrees. Sine of 90 degrees is 1. So it will be just absolute value, ILB. Okay, so we have absolute value of the spring force, ILB. So now let's write down explicitly in a vector form, and then I will take care of the directions. So first in the vector. It's outside. So right now it's just in the vector form without showing any pluses and minuses. And now let's write down relative to this x direction. So this force that way positive, this force also positive, but the magnetic force, since it points that way, negative x direction. Again, one-dimensional force is negative, it just means it points in the negative x direction. Right? Positive, it means it points in the positive x direction, or y direction, whatever directions you have. So it will be F spring plus F spring minus F magnetic equals to 0. Now I wrote explicitly all those forces with the correct directions. Again, this is negative because you see points in the negative x direction. Okay, so now we have absolute values, so let's plug it. K delta x plus K delta x plus, not plus, sorry, you didn't see this, minus I L B equals to 0. So now current appears, which we actually need to find. So now everything is in front of us. So let's analyze how many unknowns. K given, delta x given, current is our unknown. L is given, B is given, one equation, one unknown. So now we just need to solve it for current and the problem is solved. Right, so from here, ILB equals to 2K delta X. I just move this term to the other side, minus turns into plus, and then added these two terms, 2K delta X. Right? Okay, so finally, current equals to 2K delta X divided by LB. So that's the algebraic expression. And of course, if you plug numbers. Okay, I will write it down. 2 times 10 newtons per meters times delta x. 1 centimeter, it's a 10 to the power of minus 2 meters, right? Yeah. Divided by L 0.2 meters and B 0.5 Tesla. Okay, I'm not calculating. I will look at my notes. 2 amps.
How'd you get delta X again?
Delta X, it's a spring force.
Yeah,
A spring force, you remember from physics 1, K delta X?
very familiar.
Yeah, very familiar. So if you have a spring attached to the mass force, just a spring. If you compress it by delta X, your hand will experience the force equals to the spring force, which is equal to K, spring constant K times delta X. Delta X, it's a compression of the spring. So here, at this position, when the wire was over here, springs were uncompressed. And if you move it here, so springs are compressed by delta X. It's a physics 1, K delta X, absolute value of the spring force. Potential energy, 1 over 2 kx squared, K delta X squared. It's physics 1. It's essentially like a mix of physics 2 and physics 1 problem. Yeah.
Can you explain why the FM's going that way again? 'Cause I don't.
Which force?
The
FM?
Yeah.
Okay, so, here, okay, let me frame this.
'Cause I thought I was going to the right.
Okay, let's see. Direction of FM is in the cross product L cross B. L, direction of L, is determined by the direction of the current. Current is down, we know, so L vector L is down. Of course, absolute value of L is this part of the wire exposed to the magnetic field, another thing, right? So direction is down. B is dot towards you. So right hand rule now, L down. Then I need to orient, actually this is the right orientation. In this, with this position I can bend my fingers towards the vector B, which is towards you. L cross B, and you see, thumb is that way. Okay. And it must be that way because spring force, both spring forces that way, in order for this position to be an equilibrium, position, this force and this forces must be in opposite direction, right? Because then they must balance each other out. Yeah,
Can you explain where the sine 90 comes from?
this.
Yeah.
Okay, cross product. Let's say A cross B equals to absolute value. It's an absolute value of A times absolute value of B times sine of the angle between them. By definition, cross product, absolute value of the cross product.
And it's always going to be sine?
Always to be what?
It's always going to be sine?
Always, it is always sine. Because it's a, what?
Or go on? It's always sine?
Always sine. Basically, it's just a mathematical tool which mathematicians introduce for us so that we can explain directions of the velocity, to explain these phenomena.
And then
So it's by definition, all the time. If you see cross product, it's a sign. If you have a dot product, then cosine function.
and
dot
how do you know it's 90 in this case?
Because again, as we discussed, right? So L vector L is down. It's the direction of the current.
Uh-huh.
So L is down. B is towards you. You see B dot towards you.
Okay. Alright.
You see?
Yeah.
90 degrees. L, B. Okay, anything else? Awesome. Awesome. Alright, so next. Let's move to Faraday's law. So we practice this formula, this, now Faraday's law, and let's move. Again, there will be first conceptual question and then big problem. And that problem I think I gave once on the final exam. Can I start erasing? Okay, I think I can start erasing this. So that's 5. Conceptual questions. So let's say we have this uniform magnetic field. Space for more. Right. So that's B. And let's take a few loops. The first loop is going to oscillate like this. Basically, if you attach it to the string. And let me draw it like this. So let's say this is the ceiling. And here there is a cord and our loop oscillates like this. That's the loop, conducting loop. And it oscillates back and forth. So we need to answer the question, are we going to get any induced EMF and induced current? So let me, alright, so we need to answer the question about the induced current. So something not clear about the picture?
Yeah. What does it say? C with the C.
Conducting loop, C-O-N-D. Yeah. Conducting loop.
Are any of those circle X's, or are they all circle dots? The
Circle, no, only dots, circle dots, no crosses.
okay.
Right. So it's all magnetic field towards you.
Okay. Just making sure.
Okay, there are too many of them to draw, so I feel a little bit sloppy in terms of circles. Right. Okay, so in order to answer this question, so let me say this is part A, for example. Right? So let's say A. Right? For part A. So in order to answer this question, of course, we need to analyze magnetic flux to see if magnetic flux changes in time. If magnetic flux changes in time, then of course EMF is produced and current will flow through the loop. In this case, so what about the flux? So flux consists of 3 parameters, B, A, okay, let me write, so flux in case A equals to B dot A, so it's a B, A, and cosine of angle between them. So, one by one, what happens to the magnetic field? You know what, now I realize that A, we have a vector, and here A, you know what, it's not the best option. So let me use case 1, for example. 1. Okay, yeah, it's Rome 1, it's not. So, what happens to the magnetic field as this loop oscillates? Nothing. Magnetic field is uniform, right? Well, of course, we assume that there is no border over here of the magnetic field, right? So magnetic field is constant. Then area of the loop. As it oscillates, area of the loop doesn't change. We don't distort the shape of the loop. So area is also constant. Then angle, theta. Of course I can pick area vector, for example, in the same direction as the direction of the external magnetic field, so the angle will be 0, anyway, constant. Theta is 0 degrees, constant. So as a result, flux is constant in time. Flux equals to constant. As a result, EMF is going to be 0, right? Because, EMF equals minus d phi over dt. Okay, actually, let me write it down. So EMF equals to minus d phi over dt. So as a result, it's 0. No EMF, no induced current in this situation. So situation 1, no induced current. So we can say that I induced equals to 0. So it's the first situation. Now, second. Alright, so let's say we have a spring, and over here there is a loop. Again, conducting loop. So this loop moves up and down, oscillates up and down, up and down. So it will be the same. So it moves up and down. Magnetic field will be constant. Let me write over here a second situation. Right? So that is the second case. Magnetic field still constant. It moves through the magnetic field. Magnetic field doesn't change. Area of the loop again. We don't distort the shape of the loop. And angle will be also 0. I can point area vector also, for example, towards you. So it will be 0. Or if it's away from you, angle will be pi, but anyway, it's constant. So again, flux is constant. So B is constant. A is constant. Theta is constant. So again, flux is constant and EMF is 0, and of course I induced will be also 0. So trivial case, nothing happens in this case. You see that? Now, the last situation. I'm running out of space for the magnetic field. Okay, so let me extend my dots. So which way I drew it? Okay. Now, again, there is a ceiling. And now, okay, so we have this loop. And now we are spinning it around the vertical axis. So essentially it's like this. So we have this loop, and now we're spinning it. So let me write, so it's a case number 3, spinning. I think I will move over here for discussion case number 3. Again, we need to see what happens to the magnetic flux, 3 parameters, V, A, theta. Still, magnetic field, as we spin, nothing happens to the value of the magnetic field, it stays constant. Area of the loop also stays constant. We're spinning a bit, but we do not distort the shape of the loop. So area is still also constant. But what about angle? Magnetic field towards you. Let's start from this position. Area vector is also towards you, area vector, which is perpendicular to the loop, the surface of the loop. Now if I still start spinning, so magnetic field towards you. Now if I start spinning, so 30 degrees, 60 degrees, 90 degrees, 120 degrees, 180 degrees, 270, and so on, right? So as we spin the loop, the angle between the magnetic field and the area vector keeps changing. Right. So in this case, theta is a function of time. So in this case, theta is not constant. So as a result, flux is not constant, changing. So as a result, EMF is not zero, and of course there will be I induced current, which is also not zero. So there will be current, induced current. We cannot say it's clockwise or counterclockwise because in this case you're actually going to produce AC current. It is going to be over some stretch of time clockwise, then counterclockwise, then again clockwise, counterclockwise. But anyway, so the question was about
So what does phi equal?
not equals to constant. Yeah, it's my ugly constant. Basically, I assume that you can decipher my right. Constant, 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 not constant.
So not constant changing, right?
Yeah, not constant. Basically, it's a in parentheses. I can write changing in time, changing in time. So conceptually questions, almost, not almost every exam, every final exam, there are usually questions about Faraday's law because it's one of the essential laws, right? And of course we need to be somewhat familiar, somewhat comfortable with that.
This is all under Faraday's, right?
Yeah, it's all Faraday's law, right? So we move now to Faraday's law, and next will be about Lenz's rule. So now it will be still under the same problem number 5. Now let me discuss Lenz's rule. So first two situations, no induced current, but in the last situation, yeah, there will be induced current. Yeah. So let me separate it. So still number 5. Okay, so let's do this. So let's assume that we have a piece of wire. Okay, not piece, just infinitely long straight wire. Current I up. And I think something that like this there was in one of our clicker questions. And we have two loops. One loop is over here, of course, conducting loop. And the second conducting loop is going to be over here. Right, so the first one we're going to drag up. So velocity v. And the second, this one, we're going to drag that way. So we need to discuss induced current in both of these loops. I should have used similar diameter. It's not the current. Probably I will label this loop A and this will be loop B. So this is case A and this will be my case. You understand why I immediately erase it? Because A we usually use for area vector, B is for the magnetic field. Okay, situation number 1. Situation number 2, loop number 2. There's the same symbol for different quantities in the same problem, that's too much. Let me show that this is situation number 1. So first of all, direction of the magnetic field, external magnetic field, which is created by this infinitely long straight wire. Right? So magnetic field lines, again, they form circles. And directions, thumb is up, and then magnetic field is going to be here into the board, here out of the board, in it's a cross out dot. And here, cross dot dot. So that's B. Am I right? Yeah. Getting? Okay, so loop number 1. Again, we need to see what happens to the magnetic flux. Magnetic flux, B dot A. So again, analyze 3 parameters. B, external, A, and the angle. Area, obviously, as we drag the loop that way, area stays the same. We don't change the area. Constant. Angle, we can pick area vector in the same direction as the external magnetic field. In this case, angle is 0, and anyway, it's a constant. What about magnetic field? Constant or not? I can try to confuse you. Oh, look, magnetic field. The closer we are to the wire, the stronger the magnetic field is, right? Right? Closer to the source. So, for example, over here, magnetic field, let's say 5 Tesla. If you move farther away here, it will be 4 Tesla, then 3, then 2. So it looks like magnetic field is changing. So does it mean that magnetic field changes, and does it mean that we're going to get induced EMF and induced current? I'm intentionally trying to confuse you. Right?
What,
Magnetic field changing.
like for number
But-
2 is like getting.
Number 2, it will be next. It will be number 2. Right? So the number 1. Look, I'm trying to emphasize on one thing. Yeah, magnetic field changes, but those changes are in space. As you move from point to the point, magnetic field changes. But Faraday's law doesn't care what happens in space. It only wants to see if something changes in time. So yeah, magnetic field kind of not constant over the loop, right? But we're interested only what happens in time. And what actually happens in time is you drag this loop up. So if, for example, at this point, magnetic field, let's say 5 Tesla, as you drag the loop up, at that point, the magnetic field will be all the time 5 Tesla because it is at the same distance from the wire, right? It will be the same. So if this point had 4 Tesla, as you move, it will be 4 Tesla all the time. Here, 3 all the time, and so on. So at every point, magnetic field is going to be constant in time, right? So magnetic field is not changing in time. It changes in space, but Faraday's law doesn't care about that, right? So we need to see only changes in if something changing in time. So magnetic field is actually also constant, and as a result, magnetic flux is constant, and nothing happens in this case in terms of production of the induced current. So EMF will be 0. EMF equals to minus d phi over dt will be 0, and I induced also 0. So now, second loop, as Mark really wanted to jump immediately to the second loop, right? One step at a time. So again, 3 parameters. B, A, and theta. Area constant, right? So we don't do anything. We move the loop out, away from the wire. Area stays the same. We don't change that. Angle also. If you pick area vector, for example, in the same direction as the direction of the external magnetic field. So angle will be 0, and will be 0 all the time. But magnetic field, as we drag the loop away, So it will be also different in space, right? But now as we move, for example, if at this point magnetic field was originally 5 Tesla, now you move the loop out, so now it's a 4.5 Tesla, 4.3, then 4 Tesla, 3 Tesla, 2 Tesla. As we move loop away, at each point magnetic field is going down in time. Right? Of course, there are changes in space, right? But we don't care that. We're also interested in time. So in this case, magnetic field is getting weaker because you move farther and farther away from the source of the magnetic field. Of course, magnetic field is going down. So, external magnetic field is going down in time. Okay, so now Lenz's rule. So we can conclude that magnetic flux is also going down because magnetic flux is a product of B, A, and cosine of angle between them, between B and A. So now, Lenz's rule. Flux is going down. Where is Lenz? Back here. Flux is going down is this situation. So the loop becomes supportive, like as I said, compared with that historical character, Florence Nightingale. All right, so trying to support dying things, right? So, in which way? So it will start driving induced current in such a direction so that within the loop, induced magnetic field will be in the same direction as the direction of the external magnetic field, within the loop, not outside, within. So it means that within the loop, I can draw a bunch of red crosses, be induced. In the same direction, induced magnetic field will be in the same direction as the direction of the external magnetic field. So it will be induced, the same direction as B external. External magnetic field, you see that black cross in, induced also in the same direction. Now, final step, right hand rule. The second one. So we have loop magnetic field, induced magnetic field is cross, it's in, so it's this situation, right? In order to get this induced magnetic field, current must flow. So first I need to match that direction with my fingers, right? And my thumb gives me this direction. So which is, what is that, clockwise. I'm getting clockwise direction. So you see, I need to match this direction with my fingers. So I'm getting, let me check my notes clockwise. Yeah. So I induced. Again, we now looking only at the direction of the induced magnetic field. Because this induced magnetic field, since induced magnetic field is produced by the induced current, of course their directions must be connected. And we know the connections, right-hand rule. We usually use it to find the direction of the magnetic field. Outstretch your thumb, curl your fingers, but now it's a reverse situation. We know the direction of the magnetic field and we want to get the direction of the current which produced that magnetic field. A reverse situation, a reverse application of the right-hand rule number 2. Yeah.
For the number 1, since it's coming out, would it be going counterclockwise?
Oh, what do you mean number 1? This?
Yeah.
No, for the number 1 there is no current.
Oh, there's no.
Magnetic flux is constant.
All right.
The loop is happy, nothing happens, right? But in the second situation, since flux changes, right, flux changes, and of course the loop responds immediately. So it will drive current, in this case, to support dying flux. Right? So, conclusion, I induced current in clockwise direction. So, right-hand rule. Wait, Lenz's rule.
What does that say? R.
I mean right-hand rule. RHR. Come on, Mark. You're attended all the lectures. You should be familiar with these abbreviations. Of course, these abbreviations are not universal, but since I defined them at the very beginning, not at the very beginning, at some point. Okay, so now let's solve the problem. These are conceptual questions about Lenz's rule and Faraday's law. Now let's solve actually the problem. And I think this problem I gave once, I think a year ago in some. Okay, can we now switch to the problem? Make sense? So you're looking at it. Okay, now I will need the whole board, so I will paste them. Should I wait? Good? You know, it's time to change this number. Getting sick and tired of 5. Now let's switch to 6. Numbers must grow from time to time. So, U-shaped rail, but with a fancy shape. Okay, somewhat fancy shape. Let me draw this picture and then I will write down what actually is given. It's still about Faraday's law. So, one side is, let me make it wider. U-shaped rail, conducting rail, of course. Then, exposed to the magnetic field. Let's say exposed to the magnetic field. Magnetic field is represented by these dots. So it's a B external. I skipped on circles, just dots. Too many circles to draw. So B external. Looks like some kind of rush on the surface of the board. All right. Now, we need to complete the loop. In the example which we discussed in the lecture, the conducting rod was kind of perpendicular. Now let me create this conducting rod. Kind of bent. So everything is conducting, and of course there is a contact over here and over there. So in this rod can be moved, and actually we move it with a certain velocity, v. Of course, I will write down that velocity. Okay, I think it's time to start writing down what is given. So conducting rail. So conducting rail. Okay, let me write immediately the width. L, conducting rail, L equals to 0.3 meters. Then magnetic field, external magnetic field, 0.2 Tesla. Velocity with which this this conducting rod is moved, v is 5 meters per second. So velocity is given, and that's it. Yeah, just for fun, I can also give you these angles. For example, if you imagine this line, dashed line, then this angle I can say alpha and here angle alpha. And let's say alpha is given up, for example, 20 degrees, I think. You will see it's not really important in maybe 10 minutes. So, we have a loop, you see, conducting loop. Yeah,
I just have a small question. Why isn't there a vector over the magnetic field or the velocity? I was just, it doesn't happen.
okay, I'm still trying to understand why there is no vector. This vector sign?
Yeah. Okay.
My bad.
I wasn't sure if there was like a reason there.
Since, yeah, strictly speaking, there should be a vector, right? But I thought since I showed the direction of the magnetic field, direction of vectors, so kind of I was a little bit sloppy. But strictly speaking, yeah, the vector must be there. All right. So that's it. So yeah, there is a loop, conducting loop, exposed to the magnetic field. So pretty much it's possible that EMF is produced. We just need to analyze what happens to the magnetic flux and see if flux is changing and if it's changing, what's the direction of the induced current. So pretty much we just need to answer the question about the induced current. So I induced. Direction and the value. So let me first rewrite, of course, Faraday's law, since it is essential in this problem. Right. In the application of this law, we usually divide into two steps. First, or maybe second, first we would take care usually of the minus using Lenz's rule. Right? And then we can just find absolute value of EMF. That's how we usually do it. So let's start first with the direction. Direction. And so we need to repeat steps which I just erased, right, for those situations. So we need to find what happens to the flux, and so we need to look what happens to the BA and theta. Right? So let's do it. B, external again, area, and the angle. Magnetic field through the loop. This is the loop. Nothing happens. It's constant, it's uniform, so it is constant. Then area. Area, what happens to the area of the loop?
Gets bigger.
Yeah. So as we move, this area is getting bigger and bigger and bigger. So area getting bigger. Then angle. Okay, it's up to us. Since we have a freedom to choose any direction for the area vector, so I usually pick it in the direction of the external magnetic field. Towards you. In that case, area towards you, magnetic field towards you, angle is 0. Angle is 0. But anyway, it's constant. 0 degrees equals to constant. So if we combine them all, analyzing flux, B dot A, of course, flux is getting larger and larger. Magnetic flux is growing. So loop, seeing that fact that flux is growing, of course, doesn't like it, and of course, it starts rebelling. So it will start driving a current, induced current, in such a direction so that within the loop, magnetic field, induced magnetic field, will be in the opposite direction to the direction of the external magnetic field. So it means that within the loop, we're going to have a bunch of crosses representing B induced. So over here I can write that B induced is in the opposite direction to the external magnetic field. Within the loop, because again it tries to suppress the growing flux. Great, so now once we know direction of the induced magnetic field, now right-hand rule. Here's my loop. Okay, not a rectangular loop, but doesn't matter in terms of a direction. So induced magnetic field cross it's into the board, right? Into the board. Into the board, so like this, right? And in order to get that direction, I need to curl my fingers like this to match this direction. And as a result, current is going to be this way, which is clockwise. I'm getting clockwise, right? Clockwise direction. Let me check. Yeah, clockwise. So this will be I induced. So we found the direction of the induced current. So as a result, I induced CW. Okay, great. First part of the problem solved. Now, magnitude, the value of current and EMF. So now here we just need to look at the absolute value of EMF. So EMF equals to absolute value of d phi over dt. So now steps will be somewhat similar to what we had in our lectures and recitation classes. Probably, yeah, let me first write down. So let me open my explanation box. Magnetic flux equals to B external times A times cosine of angle, which we already decided it will be 0 because area vector we pointed towards us, right? So dot. So it's an angle between this B external and that A is 0 degrees. So it is equal to B external times area. So again, I close my explanation box. So as a result, we'll have minus, of course, I can drop d over dt, B external times A. Area. Area has a complicated, reasonably complicated shape, not just a rectangle, right? Area, it's a, let me label somehow, which way I label them? Let me follow my notes. Wow, that's strange. That's simple. So, point P, point M. Now I realize why I didn't use A, B, C, because A is the area vector, again, B magnetic field, right? So in order to avoid confusions, that's why I'm using such a strange letters. Not the most popular. R, F, and M. This is K. K, and M.
I have a quick question.
Mm-hmm.
Why is the internal like opposite the external? Like, why is it opposite direction?
Because flux is growing. You remember that our discussion, that system doesn't like changes. In this case, loop doesn't like when flux through the loop changes, right, in time. So if flux is growing, the intentions of the loop is to suppress the growth of that flux. So it will induce current and as a result induce magnetic field within the loop, so that we have this situation. External magnetic field this way, for example, induced magnetic field that way. So if area vector that way, then flux produced by the external magnetic field will be positive, but flux produced by this magnetic field will be negative. So we have positive flux plus negative flux. There will be what? Subtraction. If you add 5 and minus 2, the total flux will be 3. Of course, less than 5, so there is a subtraction of the magnetic flux, right?
Okay.
So that's why induced magnetic field is in the opposite direction within the loop, because intention of the loop is to suppress. If magnetic fields are in the opposite direction, flux are going to have opposite signs, and there will be flux suppression. So Yeah. So before I start applying those symbols, right? So which actually symbol can be pulled out of the sign of differentiation? B. B external. It's constant. But area is not constant. Area is a function of time. So we can't extract. It will be mathematical crime, right? Doing this. So I can take magnetic field and extract it because it's constant. Okay, so I can write it as B external and rate of change of the area. Right. So now let me write explicitly which area. So it's a B external and then d over dt. Our area consists of what? Two parts. This rectangle, which is K, R, M, P. This rectangle, right? And then triangle R, F, M. And this triangle. I can divide it, right? It's not a big deal. Area is an additive thing, additive quantity. So I can write area of B, K, R, M plus area. Okay, I'm getting close to the border where I can write R, F, M. So, if you differentiate these two terms, these two areas, which area is going to survive that differentiation without being annihilated? So which area is going to survive? Of course, rectangle. What happens to the triangle? Area of the triangle, this RFM, this triangle, RFM. As we drag this rod that way, area of this triangle in time stays the same. So if you differentiate a constant value, constant area, you will get 0. But area of this triangle, this distance keeps increasing, this R, this KR, this distance keeps increasing all the time. So area of the rectangle is growing, but area of the triangle stays the same. This area is constant, so as a result, constant, let me write over here. So dA of RFM over dt equals to 0. The derivative of that area is 0. So as a result, we'll have B external area of that triangle B. Yeah, that's strange symbols. M over dt. So now we need to somehow, actually very similar to what we did in the lecture, need to move away from this areal velocity, that's how fast area changes in time, right? To this velocity, linear velocity. And in order to do that, question?
It's again about those abbreviations.
Okay, yeah.
K, R, M. That is A, P, K, R, M.
Oh, this one?
Yeah.
P, K, R, M. P, K, R, M. This rectangle.
Oh, all right.
And then triangle R, F, M.
I got it. All right. Yeah. I see.
So, how can we make a transition? So, in order to make a transition from the areal velocity to just linear velocity, you remember the trick? We need to introduce, just for a couple of minutes, this distance. X, for example, right? Distance from this edge of the conducting loop to this point, the end of the rectangle. Just for a couple of minutes. So, let me write it down. So, explanation box. So, let's introduce X. So, as a result, that area can be written how? So how can we write that area? Area of this rectangle. If we introduce this x, area of this rectangle, L is given, yeah, width is given, length is given, so L times x, right? And now, right? So it's a L times x. Okay, so I close my explanation box, and so pretty much we're almost there. So now let's write it down instead of this L times x. So B external d over dt of L times x. So now the next step, which quantity can be pulled out of sign of differentiation? The width is constant. L is constant. So this L can be extracted. So as a result, B external times L and absolute value of dx over dt. And dx over dt, how fast this x changes in time. It's a velocity. It's the velocity with which we drag basically this rod and of course these points that way. So it's a velocity. That's the velocity. So we have as a result B external L times V. So it looks like I made system more complicated. I introduced this area of the triangle, but actually from the mathematical point of view, it didn't increase complexity. It just basically gets washed out from the calculations because area is constant, differentiated. So, of course, you can plug numbers. Yeah, I will just use my notes and write down the answer. So it will be 0.3 volts. You can plug numbers and you will get 0.3 volts. It's the EMF, potential difference, volts, units of volts. So now the last step, current. So now let's assume that we know the resistance. Of course, strictly speaking, resistance of the loop changes in time because these parts of the rod are getting larger and larger and larger, but let's assume at this particular moment of time resistance is given. So now assume R equals to, what's the value? 0.1 ohms. It's a normal value of the resistance of a piece of wire. 0.1 ohm. At this moment of time. At this time. At this moment of time. Okay, so of course, induced current. Since we know the EMF, which is somehow mysteriously produced in the loop, so you take that EMF and divide it by the resistance. So 0.3 divided by 0.1 ohm, so 3 amps. 3 amps of the induced current. Yeah.
On the exam, do we have to do all the differentiating? Can we just move right to the?
No, I noticed that students like, I know, they find it easier to just remember BLV. If you write BLV, it's not something fundamental. It's not what we're testing, your ability to remember that particular formula. So what in physics, in any other science you need to remember some fundamental formulas, fundamental equations, fundamental principle. Faraday's law, fundamental thing. So pretty much I want to see your ability of grabbing this and getting that BLV or whatever XLV. Right. So if you just write that final expression, immediately lots and lots of points will be subtracted.
So
Yeah.
why is DAR FM DT equal to 0? Again, I want to.
This,
Why is it 0?
because this area is constant,
Yeah.
area of the triangle. So
Alright.
if you differentiate any constant quantity value, right,
Yeah.
you'll get 0.
Also, that's only the rectangle is.
A rectangle, pretty much, yeah, that's what area of the rectangle, that's what bring changes in the area of the whole loop. This triangle contributes nothing. And of course, tacitly I assume that we're not discussing that moment of time when this triangle was crossing this front line, back line, because that will be different situation, different story.
So then,
Yeah.
how does dA over dt take Rn become?
Oh, because it's this rectangle. Which?
Yeah, like, and then it equals dt, it then is the external dt L times x.
I introduced this quantity x, but it's nothing wrong with that.
Oh, wait, L times, right.
Yeah, so I introduced, right, in order to make this transition smooth. Yeah.
Alright,
And so then this area of this triangle, it's L times x. Make sense? Yeah.
So yeah, I have a stupid question, but why is L then not zero if it's a constant?
Because it's a product, L times x. Here we have a sum.
Oh,
Two different things, right? Apples and oranges, right? So, all right. So if you have a constant times some variable, right? So if you differentiate it, that constant stays, and then it will be equal to constant times derivative of that function, which is in this case changes in time. But if it's a sum a plus b, and you differentiate separately first term, separately the second term, right? So different things. Here we have sum, here we have a product. Okay?
alright. So then we plug, so the external times L times V, so 0.3 meters times.
Yeah, you can plug those numbers. You will get that number differently.
Like I'm looking at it, you plug in 0.3 and then you plug in, I know that's velocity.
Mm-hmm. 5 meters per second, so 0.2, 0.3, it's a 0.06 times 5, it will be 0.3. So that's the correct number. Okay, so the next example, you can read it by yourself and practice. Now, inductors. Inductors, so problem about inductors. Then electromagnetic wave, interference. Okay, so now the part where lots of troubles. Inductance, potential difference across the inductance. So let me just repeat again this rule, Lenz's rule adjusted for the inductor, because I know at least 50% of students making mistakes on the conceptual questions about this question about the potential difference across the inductor. Right. Can I start erasing it? Okay, great. So, first I will just review the rule, adjust it, and then we will look at a couple of examples. So this will be 6. So inductors. And okay, potential difference across the inductors. So let me write, so delta V produced by an inductor. So essentially, again, I keep telling this. Essentially, it's a Lenz's rule. You just need to apply the Lenz's rule. We usually apply it for a single loop. Inductor is just thousands of loops connected next to each other. It's connected in series. So essentially, it's the same rule can be applied for those large number of loops. So as a result, instead of using what? Instead of applying like 3 steps, you will have to make like 7 steps. It becomes kind of too much. As a result, people decided, okay, let's create a new mnemonic rule in order to reduce number of steps. So Lenz's rule was about flux. Loop didn't or doesn't like when flux changes. If flux is growing, it tries to suppress it. If flux is dying, it tries to support it. Now it's exactly the same story about the inductor, but now about current, original current flowing through the inductor. If current is constant, what's the response of the inductor? No response. It's just completely happy. It's like the loop. If flux is constant, nothing is produced, no induced current. It's exactly the same story. Then if you start changing this original current, let's say you start increasing it, the inductor doesn't like changes in the original current. What's the response of the inductor? It starts producing potential difference across itself. That potential difference is produced by the solenoid. By the inductor. And in this case, since original current is growing, it doesn't like it, it starts rebelling. Like the same story, right? So it starts driving induced current in the direction opposite to the direction of the original current, trying to suppress the growth of the original current. Again, you can ask, yeah, it's cool to be a rebel, but at the expense of what? Because any rebellion, right, takes lots of money, right? In this case, so where is the energy? Where is the energy to do that? And energy, when I introduced inductance, I told you the role of the inductor, it allows us to store some amount of energy inside of the inductor in the form of the magnetic field. That energy can be used to rebel or to support. Inside of the inductor, there is some amount of energy. So, and now using that energy, in this case, it drives induced current in the opposite direction to the original current. And then once you know the direction of the current, you can get information about the potential difference, because current flows all the time from plus to minus. We all know that, right? And in this case, if current is dying, then induced current is in the same direction, supporting dying current. And then once you know the direction of the induced current, you can get information about the potential difference, because again, this current flows from plus to minus. Now let me draw some diagrams and show that on the pictures. So, and again, philosophical idea, L does, what's the symbol is that? I have no idea. Does not like, okay, let me put it like this, quotes. Does not like when original current I naught changes. It's like with the flux. And now let's look at these three situations. So let's say this is our inductor, right? And so let's say current, original current goes this way. So that's I naught, which is driven by some battery over here. There is a battery which drives this original current through the inductor. Yeah? Yeah, as like a few minutes ago, we discussed that GoPro started giving me some hard times. Right? Yeah, it showed the message that there's something. Oh, now it fixed the file, finally. Cool. So now it's working again. It was actually really fixing something. So this is, you remember, according to the rule, this is the final point, because current exits the solenoid. This is initial point, right? And so if this original current is constant, then solenoid is happy and it doesn't do anything. It doesn't produce any potential difference across itself. So in this case, it's just a useless long piece of wire in your circuit which doesn't do anything. So if it is constant, then L inductor, right, does not produce any potential difference, any delta V across itself. So delta V will be 0. So it means that electric potential at point I and point F will be exactly the same. It's just a piece of an ideal wire, we assume. It doesn't have any resistance. Vi equals to VF. So it's a situation when nothing happens. Now let's start changing current. So that was the first case, now the second. All right, so let's say this is our inductor. All right. Again, this is our final point. This is our initial point and original current. And let's say now original current increases. So if I not increases, then inductor doesn't like this. It is happy when current stays constant. So what's the response of the solenoid in this case, of the inductor? That's what I wrote over here. So in this case, it rebels using its internal energy. So it means that the induced current will be in the direction opposite to the direction of the original current. So let me write underneath it, rebels. So it means that induced current is going to, okay, original current what? Counterclockwise. Induced current will be clockwise. Induced current in this case will be clockwise. So clockwise, it's this way, right? So I induced. And now, after this, once you see the direction of the induced current, you should be able to tell me where is the electric potential higher, at the final point or at the initial point, in order to get this direction of the induced current. That potential difference is the source of this induced current. So since current starts here, so it means that over here there must be some kind of plus at the initial point, right? Higher potential, and lower potential over there. Again, quite often, in order to reduce chances of making mistakes, I usually suggest, imagine that sort of introduce like a fictitious battery instead of this solenoid. So now a solenoid starts working as small fictitious battery, right? So with this polarity, so let me write, so plus and minus. So with this battery, it drives the current in that direction. So it means that the final point has plus, initial point has plus, final point is at minus. So in this case, delta V is final minus initial, so it will be negative. Delta V is negative. So now delta V is negative, so V final is less than V initial. So essentially that's what in this line, that's what I drew in this line. Sometimes the train of thoughts can be in the opposite direction. For example, sometimes potential difference is given. It's like in one of the clicker questions in the lecture, right? So potential difference is given, so pretty much you start from this and you need to move in the opposite direction. So potential difference is known, so you can imagine what's the direction of the induced current. Not imagine, you can draw. And then, since it's usually direction of the original current is given, so you see directions are the same, it means that the system's supporting dying current, so it means that the original current is dying. If directions are opposite, okay, so it means that it's rebelling, so it means that the original current was growing. So you see pretty much you just apply the same train of thoughts, but in the opposite direction. So it depends what is given. Sometimes you have information about the original current, you move this way. Sometimes potential difference is given, you move that way. It depends on the situation. We will look at a couple of examples, right? So right now I just want to discuss the rule. All right. So and now the last situation, what if the original current is, what if original current decreases? So this is again our inductor, right? Again, the original current is going this way, let's assume, but now I naught decreases in time. Again, so our inductor is not going to like it if I naught decreases, because it wants to keep current as constant as possible. So in this case, I induced will be in the same direction as the original current. So it means the same direction, so in original current counterclockwise, so induced current will be also counterclockwise. So it means that it's this way, right? So you see that direction, now it's this direction. You see, it's up, up, clockwise, or counterclockwise, both. So you see, the same directions. So now again, imagine about some fictitious battery. How should you orient that fictitious battery, polarity of that battery in order to get this current? Obviously, here it should be plus, and here it should be minus. So it means that this point is at higher potential, that point is at lower potential. And again, this is our final point, and this is our initial point. Final and initial points are determined by the direction of the original current. So now we can get to the potential difference. So that's what I drew or wrote over here. So now let's look at a couple of examples. Essentially, it's the same, it's Lenz's rule. We just sort of adjusted, abbreviated, right, modified to make it easier to apply, to analyze inductors. So, okay, I prepared this. I used to discuss it in a lecture in one of the clicker questions. So, example. Oops. I think it's one of the examples from one of the exams. So we have this picture. So this is battery which drives this original current. So what happens to that current? We know its direction. So let me look. Resistance shown. Yeah. The current, original current is given. So this is I naught, and we know that this current increasing. Given. So this is given, let me write, it's given. So then 2 points before and after the inductor. So let's call this point A and this point B. So now the question is, which point A or B is at higher electric potential? So the question is, which point A or B is at higher electric potential? And with the questions like this, as I said in the past, lots of like 50% of mistakes, because usually students most of the time just guessing this case. That's why previous year or previous semester I started discussing more of this rule on the exam review session, because something needs to be done, because what we discuss in the class is not enough. Right. So let's start basically looking at this train of thoughts, one of these train of thoughts, which one fits. Right? So original current, okay, since original current is growing, it's given. It means that what's the response of the inductor? It hates it, right? It rebels in this case. Original current is growing, so something must be done to suppress it, right? So in this case, it rebels. So it means that I induced will be in the direction opposite to I original. So let me write it rebels. So now, since we know direction of the original current, we can draw on the picture the actual direction of the induced current, opposite. So since original current counterclockwise, so the induced current will be clockwise. Well, you know what, let me draw it. Since the source is the inductor, so let me draw it this way. So this is counterclockwise, so it should be clockwise. So it's like this, right? So this is I induced. And now we know this current is produced inside of the inductor. It flows from plus to minus. Again, imagine some fictitious battery in order to get this direction of the current. So fictitious polarity of the fictitious battery should be like this. Plus at the bottom, right? So over here it should be plus, and here minus. Only in this case, this induced current, of course, produced by this fictitious battery, but of course it's inside of the solenoid using that internal energy of the inductor. So it means that point A is at higher electric potential than point B. Only in this case, we can get this direction of the induced current. So that's the logic. But usually students in the past, they just they think that this battery determines and determines the potential difference. No, we assume that this solenoid is made of an ideal ideal wire, so it doesn't have any voltage drop. So it means that after this, we can write that point A is at higher electric potential than point B. So basically delta V. So it's not a rocket science. You just need to sort of get used to this idea. And VA is larger than VB. Yeah. Make sense? Another example. Okay, let's just quickly. I'm just making it up. I haven't prepared that. Another example. Something like what we had in our clicker questions, one of the clicker questions in the lecture. So let's assume that we have an inductor, right? And we know the direction of the original current. So let's say this is I naught. But we don't know what happens to this current. Just we don't know. But we do know that electric potential at this point, at the end of the solenoid, is plus, and over there minus. All right? So again, this plus and minus, that's what something happens to this current, and this inductor produces. It's made by the inductor, produced by the inductor. So now, what happens to this original current? We need to see what's the direction of the induced current. So again, imagine fictitious battery. So this is plus, this is minus. So you can imagine something like this. So it's a plus minus. And now, obviously, what's the direction of the induced current? From plus through the rest of the circuit to the minus. I induced. So directions of the induced current and direction of the original current are the same. So it's possible only when the original current is dying, the system becomes supportive. It's supporting dying current. So pretty much over here, now you see I'm moving in the opposite direction. In this example, we move from the information about the current to get delta V. Now delta V was given, and you move in the opposite direction to get information about the original current. So it's exactly the same rule, but we're just moving back and forth, depending on what is given. So it means that, let me write, so since I induced is in the same direction as I original, so it's supportive. Wait, what did I write? Supportive. So we can jump to the conclusion. Yeah, so it means that original current is decreases. Original current decreases, right? Calculations of the potential difference using this formula. there is one example. I just don't want to write it. It's you just where is it? Yeah, this. Inductance is given. Initial current is given. Final current is given, and the period of time over which this current changes is given. Just calculate, and you will get the potential difference across the inductor. Right? So I will skip this example. So it's just plugging numbers. Again, the problems are in the conceptual explanations. That's where troubles are. Basically, it was like 50-50. Sometimes people you can guess sometimes. Not right. Yeah.
For the like third case scenario, does the voltage, the final voltage increase?
So what's the actual conclusion? Or yeah, I decided to skip. So in this case, so you see final point is at higher potential. So let me write. So V final is larger than V initial, right? So delta V is actually positive. So here delta V is negative. Here delta V is positive, right? Again, the logic why I started introducing this fictitious battery, because quite often students see plus and minus, and now it looks like, you see, they kind of spread this plus and minus. So they know that current must flow from plus to minus. But they draw it through the solenoid, that current. No, current must flow through the rest of the circuit, right? So that's why I'm trying to sort of squeeze the gap, right? Reduce the gap between this minus and this plus, so that students was not tempted to draw the current in the wrong direction, right? Plus and minus, and then through the rest of the circuit. Right? It's like in my recitation classes, I usually compare that with, I don't know, a production of something like a smartphone. So there is a production line. So here the ingredients, here the final product. Minus plus, production line. And then you send those phones through the rest of the circuit, through the world, through all the consumers, right? You're not sending them back, trashing them back to the ingredients, right? So you send that product through the rest of the circuit, right? Whew. So, EM wave. So what do we know about this electromagnetic wave? Propagates in z direction. Propagates in, plus z direction. Then, electric field points in the x direction. Okay. So we'll have to write E as a function of, I don't want to write immediately, because I will write the answer immediately, part of the answer. So let me write math expressions of E and B. Okay. Another thing, frequency is given. F is given, 60 Hertz. Sorry guys, I don't know why I picked such a low frequency, because as a result, wavelengths will be really scary, gigantic, really huge. But again, it doesn't matter. It's still possible, it exists in the nature, so not very common maybe. Right, so let me first write this expression without knowing K and W, right, in order to analyze directions of directions. And you know what, even before I start writing that down, let me draw the picture. So, this axis, it propagates in a z direction, so this is z. Then, of course, let's pick a right-handed coordinate system. Right-handed, it means if you take a cross product of x and y, you should get z direction. So in order to get x cross y and in the z direction, so this should be x and this is y. So x cross y, you will get positive z direction. So right-handed coordinate system. So electric field oscillates in the x direction. So electric field oscillates up and down. So let me draw it. And it's a sine function. So let me use sine function. So it will be something like this. So that's electric field. Then, magnetic field. What's left for the magnetic field? Which direction is still unused? Y, right? So because you remember, these three directions, E, B, and V, they must be perpendicular to each other. So velocity in this way, V, E in the x direction, so magnetic field must be in the y direction. So that's magnetic field. So B. So that's the picture, and now let's actually start writing down mathematical expressions. So let's start with the electric field. So E equals amplitude. On purpose, I'm skipping some very important steps because I want to discuss that. Okay. Okay, enough. Too many gaps. So first, subscript next to the electric field. Which subscript should we use here? Should we write here? That's the first place where lots of troubles, lots of mistakes. In this case, actually, it's written electric field oscillates in the x direction. Electromagnetic wave is a transverse wave. Sort of like a wave on a cord. Wave on the cord propagates, let's say, in the horizontal direction, but particles moves up and down, up and down. So the same with the electric field. Electric field up and down, but the wave propagates in the z direction. Electric field oscillates in the x direction. Over here, we must put x. It's a first place for lots of mistakes, right? So but the wave propagates in the z direction. So k. So now which variable we have to write over here? Of course, z. Right? Z. It's the direction of wave propagation. Z. Then plus or minus. Minus because it propagates in the positive z direction. So minus. So omega and time, nothing special about time. Time doesn't have any directions, and so on. It moves only forward. Then initial phase, this initial phase. You know what, guys? Most of the time when we work, when we work with electromagnetic wave, most of the time we're not interested in the initial phase, right? So usually it's a fast oscillating waves, right? And usually in experiments, we're not interested in the initial phase. Although it's still possible situations where you might be interested in the initial phase. All right, so here, let's assume we don't care about the initial phase. It's zero. At the initial moment of time, the wave goes through the origin. Initial phase is zero. Actually, additional question which I forgot to ask. Is this a history graph or snapshot graph? It's effectively a photograph of the wave. If we could take a picture of an electromagnetic wave. So you see we have Z. It's a snapshot graph. It's a snapshot graph. Let me write that down. So it's a snapshot graph. Oh, for example, let's say taking a t equals 0 to justify that there is no initial phase in my mathematical expressions. Now everything matches. Great. So now, what about magnetic field? B. And now subscript must be y. B sub y equals to V naught. And as I said at the very beginning, both of these waves, electric field traveling wave, magnetic field traveling wave, they oscillate in unison. So it means that z and time dependence in this case exactly the same. So you just, if you have an expression for the electric field, for the magnetic field, you just need to rewrite this here. just copy and paste. So this part, sine kc minus omega t, is exactly the same over here. All the time. So sine kz minus omega t. So this part, exactly the same all the time in the electromagnetic wave. So pretty much differences only in the subscripts, amplitudes, and of course instead of E you need to write B. Okay, so now electric field amplitude is given. We will have to find B naught, we need to find K, and we need to find omega. Basically 3 parts. And that will be the end of the problem. So let's start with K. So by definition, K it's a 2 pi divided by lambda. Wave number, K is a wave number. By definition, 2 pi divided by spatial periodicity. But do we know the wavelength? Not yet. Actually, the wavelength over here, it's just because it's a snapshot graph, so this is actually lambda. This is lambda. Okay, so, but we know it's electromagnetic wave. Although kind of low frequency, but electromagnetic wave, and it propagates with the speed of light. We know speed. We know frequency, so we should be able to find wavelengths just like that. So, since V equals to lambda f, and of course V equals to the speed of light, so of course from here we can get lambda equals to c divided by f. Now I will plug numbers and don't get scared because the wavelength is going to be really gigantic. Okay, low frequency 60 hertz electromagnetic wave, really gigantic wavelengths. 3 times 10 to the power of 8 meters per second divided by 60 hertz. Okay, hertz, it's 1/seconds. Okay, let me use my notes. So it's 5 times 10 to the power of 6 meters. Don't try to imagine it.
660, what is that?
60 1/seconds, hertz.
Oh.
Right. Just in order to see seconds, cancellation of seconds. So it's a gigantic velocity. Oh, it's wavelengths. All right. Okay. So now, once we know wavelengths, of course, we can find k. K equals to 2 pi divided by 5 times 10 to the power of 6 meters. I think I used
That's the length, right? Wavelength.
wavelengths here. Lambda wavelength. It's almost like a universal convention. Wavelengths, lambda. So it will be 1.26 times 10 to the power of -6 inverse meters. So that's the wave number, spatial frequency, effectively wave number. Okay, we found K. Now, next, omega. So let me probably put here the first bullet, K. Now, what about omega? I would probably start again from the definition. We introduce K and omega in a very similar way. So omega equals to 2 pi divided by t. Period is not given, but we have frequency. And they are reciprocal of each other, t and f, right? So of course we can write it as 2 pi f. 1/t, it's f frequency, right? So pretty much we just need to plug numbers. I don't need to know it's 60 hertz, so it will be 120 pi, or maybe, yeah, actually calculate. So 2 pi times 60 hertz, so it will be 377 radians per second. So what's left? What's left? B naught. Magnitude, amplitude of the magnetic field. Amplitude of the magnetic field. So B sub 0 We just need to remember that amplitudes of the electric and magnetic field are deeply connected through the speed of light. Electric field amplitude is way larger than magnetic field numerically. 8 orders of magnitude. So we just need to remember that E naught equals to C times B naught. Again, it can be shown mathematically when we move, if you move from the Maxwell's equations to wave equations. But we skip that. I just told you that these amplitudes are connected to the speed of light. Okay, so we need to find B naught. So it's a electric field amplitude divided by C. So it's a 20 volts per meters divided by 3 times 10 to the power of 8 meters per second.
Isn't it 2?
2? Oh, yeah. I don't know where I get 20. It's evening, Friday evening. I saw it somewhere today, some 20 somewhere. Okay, maybe in the previous program.
That's
Come on,
two-
some interferences in my head that happens.
2 volts per meter, or was that 2 over,
Volts per meters.
no, volts per
Yeah, it's good. Correct. All right, so, okay, the answer is going to be 6.67 times 10 to the power of minus 9. Okay, units of Tesla, of course, we know that you will end up with Tesla. So, that's it now. We just need to write down the expression. But you know what? We found everything, so you just need to plug the values. Okay, problem solved. Right. So just rewriting this with the numbers, it's waste of time. But of course, if the problem asks, write down in terms of, no, actually I would never subtract the points. If you find everything and write in the symbolic form without plugging numbers, yeah, I can buy it. Okay, so now, problem about interference, it's not complicated. So it says 2 out of phase radio antennas. Speakers can be also acoustic waves, right? But of course, usually if a problem about acoustic waves, speed of sound is usually given. Give or take 340 meters per second. Right? Depends on the conditions, temperature, and so on. Radio antennas frequencies are 300 megahertz. One frequency is given, although there are 2 antennas, because we're discussing 2 identical waves. It means that they have the same amplitude, the same frequency, the same wavelength, pretty much 2 identical waves, just they are produced by 2 different sources. Right? Only in that case we can apply the formula, conditions which we derived. So, and now let's say this is antenna number 1. So let's say it's here, right? So it's antenna first, right? And then the second antenna is here somewhere. Again, physics is this antenna essentially produces, of course, it produces spherical waves. But if you look at the cross section, right? So you're going to basically see cylindrical, not cylindrical, circular waves. So this. Right. And actually, what I just drew, these lines, how do we call these lines? Huh? Wave fronts. Wave fronts. Essentially, these are wave fronts, which represent a collection of crests. Again, wave, it's sort of a crest, trough, crest, a trough, crest, trough. So wave front, it's a collection of crests. Right, so these are wave fronts. It's not that essential for this problem, but anyway, wave front. Right. So the second, this first wave, the first source produces its own wave, and these are wave fronts of that wave. And so, since they're identical, so over here, the whole field will be filled with bright and dark spots. If you start, for example, over here, right? So there will be bright spot over here, point of constructive interference. If you step away, there will be point of destructive interference, that again constructive, then again destructive, then again constructive. You move this way again, destructive, constructive, destructive, constructive. So essentially we have an infinite number of possible bright and dark spots in this field. So you can move with the antenna getting large signal, noise, large signal, noise, right, and so on. Yeah.
So by looking at that, where exactly are the bright spots and where exactly are the dark spots? Can you tell just from looking at like this?
I can tell that by looking at this picture. In your recitation classes, you discuss problems like this. So look, if you take, for example, this point, you see intersection of this wavefront and that wavefront. What are you going to get over there?
Bright spot?
It looks like you're guessing. Guessing. So what is at the wavefront? Crest or trough?
Crest.
Yeah, crest. So essentially we have a blue crest, and on top of that we have a green crest. Two crests, what are you going to get? Constructive interference. Of course, you're doubling amplitude. That's what essentially constructive interference, right? So essentially you have something like this, right? So you have one wave, and then on top of that you have the second wave, right? So you see, this is the point, crest over crest, constructive interference. Then if I take, for example, this point, what are you going to get at that point?
Dark spot.
Huh?
No, they're both troughs, so it'll also be a bright spot, right?
Okay, great. Right, because quite often students jump to the conclusion about destructive, but it's not, because you essentially have trough over trough. You're between the wavefronts, it's a trough, blue trough, and between the wavefronts, you are in the green. There is a green trough over there. Trough over trough. It's exactly the same like crest over crest. It gives you constructive interference. Yeah, by looking at this, I can tell you. I can tell that. But the thing is, we don't see these wavefronts if you are somewhere in the field, right? With two radio antennas. All right, so essentially it's better to calculate, make some calculations, some predictions, and you can go and actually confirm that, right? Right. So now the problem asks, gives a particular point. Let's say point is somewhere over here, and these distances are given. So for example, this point. And geometry is very simple. I didn't want to make it more complicated. So the distance from the second source is R2, 5 meters. So I just simplified, just in order to apply that condition without any geometry. And let's say the distance from the first source is 2 meters. So, and somewhere over here, somebody is standing, right, with the antenna, trying to see, is it constructive or destructive interference? Right. Okay, so we just need to grab the condition which we derived. Spent like half an hour, if not more, deriving that. It was a little bit tedious. So delta phi equals to 2 pi over lambda, the path length difference plus the inherent phase difference, and then if it's an integer number of 2 pi's, then it's a constructive. If it's a m plus 1 over 2 pi, then it's a destructive interference. So we just need to check this condition. So first, path length difference. So delta r. Again, what's the meaning of path length difference? It's just an additional distance that the second wave has to cover on the way to the point in question relative to the first wave. That's it. It's very simple meaning. One of the lengths is longer, so what's the additional distance? So in this case, again, I simplified geometry to the simplest possible, so it's just R2 minus R1. R2 minus R1, so 5 minus 2 meters, so it's 3 meters. So additional distance that the second wave has to cover relative to the first wave is 3 meters. Right. Okay, so this is done. So now inherent phase difference. What's the value of the inherent phase difference?
And that's where the problems are usually on the exam, right? So in the recitation classes we discussed, usually that information is hidden in the statement of the problem. And on purpose, I kind of lazy to write. And in this case, I wrote, you see at the top, 2 out-of-phase antennas. Out of phase, it means that the author or the who wrote the paper or report or the problem, right, wants to tell you that these antennas were wired in such a way that the phase difference, initial phase over here, for example, 0, initial phase over there is pi. So that the inherent phase difference, what is essentially inherent phase difference? It's a difference between initial phases. Initial phase of the second source minus initial phase of the second source, or of the first source. That's the meaning of the inherent phase difference. So in this case, since it says out of phase, it means that delta phi naught is 0. So it means that delta phi naught equals to pi. And that's where troubles are. I don't know what the reason, but whenever I give a problem like this, I don't know, 30% of students at least assume that it's 0. They just ditch that delta phi naught and solve the problem, of course, in the wrong way. So inherent phase difference, inherent phase difference. And why it's called inherent? Because it doesn't matter which point you pick, this point, this point, this point, any point, that delta phi naught will be exactly the same for the whole field. It's determined by the initial phase of this and initial phase of that. It's basically how you connect, I don't know, a function generator to your antennas to drive the current through in your antenna. And these days you can easily change the initial phase, right, of the function generators. Now they're quite fancy. So inherent phase difference. All right, so delta phi naught, it's essentially phi 20 minus phi 10. And from the statement of the problem is pi. Pi from the problem. Out of phase antennas. If the problem was saying in-phase antennas or identical antennas or sources, it should trigger immediately your brain, aha, inherent phase difference is 0 in that case, right? Or I can give you something like this. Let's say phi 20 equals pi, phi 10 equals 0. In that case, I can skip these words, but you can see, so they're obviously out of phase. Inherent phase difference is pi. So easiest part, but most of the troubles are here. Yeah?
So can that value only be pi or 0?
No, usually in this course, we usually try to simplify only those extreme cases, but it can be like pi over 2. Again, it's up to you. It depends what you want to achieve. It depends how you wired your antennas to connect it to the function generators, right? It can be sine and cosine pi over 2, the phase difference, right? It can be 3 pi over 2. It can be 2 quarters or 2/3 of the pi. Anything can be, right? But usually at this case, in order to sort of develop the habit of getting it correctly, right? So just sticking to the 2 cases, in phase, out of phase. Right. So what else? What else must be found before we can start analyzing? We know delta phi naught. Wavelength. Yeah, wavelengths. Wavelengths must be found, right? So now the last piece, wavelengths. So, and again, it's a radio antenna. So electromagnetic waves, we know speed of light. They propagate with the speed of light. So C divided by F. So I'm just using this. Yeah, V equals lambda F. So, and V is the speed of light. So 3 times 10 to the power of 8 meters per second divided by, what's the frequency? 300 mega secs, 10 to the power of 6, right? Times 10 to the power of 6 hertz, it's 1 over seconds. Ah, it's just one meter. Yeah, it's a nice number. I forgot. Right. So it's essentially 3 times 10 to the power of 8, 3 times 10 to the power of 8. So it's 1 meter wavelength. Right. Okay, so we're all set. Now we just need to put these ingredients to the same pot, right, and start analyzing. Right. So 2 pi over, okay, so that's delta phi. Now I'm analyzing this condition. 2 pi divided by 1 meter times the path length difference is 3. And plus the inherent phase difference, which is pi. Six pi plus pi, 7 pi's. And conclusion. Constructive, destructive. Huh? Destructive. Huh? You're guessing, right? So, we'll just analyze it carefully, right? So, who thinks destructive? Okay, almost 50-50, right? Okay, it's a very common. It's a very common. Now let me, I've done it in my recitation classes exactly the same, right? Because I noticed every semester, almost like 50-50 at that point, students pick the, okay, I don't want to say which, wrong or right. Look, guys, this is, we have odd number of pi's, odd. And okay, yeah, those who picked destructive, okay, good. All right. So now, those who picked constructive option, they usually logic of U sort of like this. So it's a very simple expression, just in terms of structure. They look, okay, it looks like simple. Now they're looking at this, which of these constructions are simple? And they see, oh, it looks like this is also simple. So and they're matching simple with simple. And they claim it's a constructive interference. And but it's a wrong option because, look, we have odd number of pi's, but here we have what? 2 times integer. You can multiply any integer by 2 and you're going to get even number. You will never get odd number. So it means that this condition is impossible. Constructive is impossible. You see? Because every time if you multiply any integer by 2, you're going to get odd even number. But we have odd number of pi's. So definitely constructive is out of the question. It's still possible something in between, right? Who knows? But so let's look anyway at the destructive because it looks like the only option, right? Unless it's something in between. So m plus 1 over 2 times 2 pi. Okay, so let's start checking. Again, m is an integer from 0 to infinity. M equals 0, so it will be 1 over 2 times 2 pi, pi, not our case. M equals 1, 2 over 2 plus 1 over 2, 3 over 2. It gives us 3 pi. Not enough. We need to go more. 2, so it's a 4 over 2 plus 1 over 2. 5 over 2 times 2 pi, so it's a 5 pi. Not enough. 3 over 2. 6 over 2, sorry, 6 over 2 plus 1 over 2, right? So yeah, we're getting 7 over 2. So this is correct for an integer m equals 3. So this condition, we satisfy this condition, right? So that's how it is done, right? So just analyzing, right? Yeah.
So are delta R and M the same, basically?
Delta R and what?
Oh wait, so how do you know that M is 3? Just because
I'm just checking, I'm just fitting it. So I know that m, in these conditions, m is an integer. It is 0, 1, 2, 3. So because you remember we discussed over here, so there are infinite number of bright and dark spots. We need to give them a certain m. So if you start over here, let's say it's m equals 0. If you move this way, so it will be m equals 1, m equals 2, m equals 3, and so on. So pretty much we associate a certain integer with one of those bright and dark spots. So it's just one of the dark spots with integer m equals 3. Right. So you just write it and then see, can you get that number with a certain value of m? Right. It's definitely impossible with these m's, because as I said, every time you were supposed to get even number of pi's. Right. So if this is not possible, then of course let's check that one. And it actually it's possible with you. We can feed that. So that's how it is done. Right. And as I said, most of the mistakes are over here analyzing, jumping to the conclusion, and in the inherent phase difference. These are two spots, right? Usually geometry, path length difference, no troubles at all. Right. So, yeah, I didn't write the conclusion. So it's a destructive interference, D. Any questions on this? Okay. Of course, if I give it on the exam, I will give some geometry, maybe some distance over here, some distance over there. Usually just a Pythagorean theorem you have to apply a couple of times, right? So usually banal.
For a problem like this, what would be the question state? Like what is it? I guess I'm kind of confused what it's asking for.
Okay. So we picked a certain point. Right. So to that point, this distance is 5 meters, and from this source is 2 meters. So we just need to analyze this point. If you stand over there, what are you going to get in your antenna? Strong signal with the amplitude, which is double amplitude of this or that. Or you're going to see, just see the noise only. Pretty much it means nothing, no signal. It means the destructive interference. So essentially, we want to analyze this point. Are you going to get strong signal with doubled amplitude or just a noise? Right. So in this case, it looks like we're getting into the noise point. Pretty much at that point, you don't have signal. Right. But if you move yourself slightly, for example, to this point, you will get constructive interference with a strong signal. Then if you move farther, then destructive again. And then again constructive, and then again destructive, right? And you can move in any direction, and every time it will be constructive, destructive, constructive, and destructive. Between them, of course, there will be something in between, right? Because first you will going to have here 0 amplitude. At that point, there will be 2A amplitude, but between them, of course, something in between, right? So from 0, it will be for small signal, then getting stronger and stronger and stronger, and then to the maximum, and then again to the minimum. And then again to the maximum, and then again to the minimum, right? So, all right. 3 hours, okay, good. Probably the last conceptual questions. In my recitation classes, I discussed just in the morning. Probably in your recitation classes, you discussed it in previous week. But since I quite often give questions like this, I want to discuss it here. And then probably we'll call it a day. I don't want to discuss double slit in diffraction grating because we just solve problems in the morning, right? So these are conceptual questions. You know what? I will keep it. I will just separate it like this. And so that was 8. We can call it 9, but it's a conceptual. So about essentially these wave fronts, because I notice it takes a little bit of time, a little bit of pushing in order for you to remember that. So let's assume that we have 2 sources of circular waves. So let's say source number 1, which generates this circular wave front. Essentially, it's sort of like a swimming pool. And you poke your finger somewhere in the middle, right, with the same frequency, right? What you're going to see? You're going to see a bunch of circles, right? And sort of by convention, we use collection of crests to visualize these waves. collection of crests, we call them wave fronts, not collection of troughs, right? Usually I told them, students, that any psychologist will tell you, use something bright, be on the positive side, be positive. So crests, bright things, right? So it helps to remember it. So then this will be the wave front, another one. So again, these are wave fronts. And so essentially the wave fronts, we have crest, then trough, then crest, then trough, then again, right. So collection of crests. Crests. And then the second wave, so which is produced by this source S2 and identical. It means that amplitude the same, wavelengths the same, frequency the same, so they propagate, they live in space and time the same life. And so these wave fronts. Okay, they're a little bit ugly, but I do the best. I usually tell it's a modern art. It's the way I see it, right? You know, like modern art is to justify everything. That's the way I see it, right? Shut up, right? So, and now let's analyze a few points. Again, you've done it in your recitation classes, but I just want to emphasize on that. So, if I, for example, take this point, I know, A, and we talked about that essentially with you like 10 minutes ago. Again, so what are we going to see at point A? Again, I pick some point in space, and I want to analyze. Essentially, that's what we've done over here. But now we just want to analyze conceptually without getting into the to numbers, right? So, and of course, at that point, we're going to get constructive or destructive? Constructive, because we see intersection of two wave fronts. It means that we're going to have blue crest on top of black crest. Two crests together, of course, they're going to double your amplitude, giving you point of a constructive interference. So at point A, we're going to see C, constructive interference, right? Crest over crest, I can write. So it's essentially crest over crest. I'm not supposed to cross this line because that's the end of field of view of the camera. Right. So now, then if I take, okay, I can move to this side. So if I take, for example, this point, let's say point B, constructive or destructive? Of course, again, constructive. Now it's a trough over trough. But again, what's the difference? Crest over crest or trough over trough, the same physics, right? So over here, we're going to see a point of a constructive interference, C. So it's a trough over trough. And the last point, because there are only three situations possible. Right? Of course, we're not discussing something in between because it's something in between not interesting. Usually we are in our applications where we want to either amplify something to the largest possible, or we don't want to hear anything, like a noise cancelling headphones. Essentially, these interference conditions are used. Basically, this is used, right? So they get the signal from the outside world and then generate the second signal, which is out of phase, and send it back into you. Send it into your ear. So you have two signals. So you basically, instead of one signal, you have two signals. But since they're out of phase, they basically kill each other, right? So and you hear nothing, right? So that's how any normal headphones, noise canceling headphones, are working, right? Using this situation. So, and the last point, okay, I didn't pick it, so which, okay, this, let's say this point. All right, so point C I cannot use. Let me call it point D, of course, also cannot use. R. So, and now, obviously, constructive or destructive? Need to think. Okay, again, think it in terms of wave fronts. and what does wavefront represent? So essentially we are on a black wavefront, so it means that we have black crest. And we are between blue wavefronts. Between, it means that blue trough. So we have crest over trough. What's the result if you overimpose, right? So crest over trough, destructive. They completely cancel each other, right? So there will be no disturbance of the medium at that spot, right? So yeah, of course, it's a point of destructive interference. So D. So it's a crest over trough. So destructive interference, right? So by just looking at the picture, you can easily jump to the conclusion. Okay, so now next situation. No, I have to erase it. Okay, so now what if you take this, for example, blue wave, and let it propagate to infinity? So what if R goes to infinity? Okay, R is a distance from the source. Which wavefronts of which shape are you going to observe? If you, yeah, of course, strictly speaking, it's still circular waves. But if you sit over here and look around yourself, you're going to see actually curvature, right? Curvatures, right? So you can see those circles. But if you let it propagate to infinity, if you look around yourself, you're going to see essentially straight lines, bunch of straight lines. Again, what is a straight line? It's a circle with an infinite radius, right? So if you let these circles propagate to infinity, you're going to get a circle with an infinite radius, and that's what a straight line is. So essentially, you're going to see bunch of parallel lines, straight lines. Blue, these. So essentially, these are wave fronts of that blue wave if you let it propagate to infinity. So these waves are called plane waves. If you use laser light, usually wave fronts has this shape. So plane waves, right? So these are wave fronts. And again, it's a crest, trough, so all that story, all those stories. So plane waves. And so now let's superimpose it with the black. Okay, I exaggerate, I increase the angle slightly. Right. So now let's assume that we have, okay, let me use green because I use black. So now let's say we have another wave propagating this way. So this is the velocity of the green. This is the velocity of the blue. And I can ask you exactly the same questions. I can pick any point, like over there. I can ask you the same questions, and the analysis is exactly the same. Where are the crests, where are the troughs? So, for example, if I take this point, point A, so we're going to see, obviously, constructive interference, right? Crest over crest. If I take this point, so trough over trough, still constructive interference. If I pick this point, now it's a trough over crest, destructive interference, right? So situation, this situation and that situation, they're essentially the same. It's just it's a circular waves at infinity, right? So this is destructive. Plane waves. Interference of two plane waves.